Right, we're going to look at the normal distribution or the standard normal distribution. So the thing about this is that if our data is normally distributed, what that means is it creates this bell curve here, right? And that it's pretty symmetrical on both sides. There's not any skewing to either direction. So this normal distribution has some properties with it. So it's usually centered at the mean. In this standard normal, though, all of the data values have been standardized, or we've gotten everything in terms of z-scores. So our mean in a standard distribution is 0. And then we taper out from that. And just a normal distribution, you would just have your mean, whatever it is, and then you would have actual values for those standard deviations on either side. On the standard, we just have the 1, 2, and 3, and the negative 1, negative 2, negative 3. So some properties about this bell curve is that typically within one standard deviation, 68% of the data is covered, which if we split it in half, we get 34 and 34%. Right. If we go out a second standard deviation from the mean, we now cover 95% of the data, right? So I could split it. I don't know if I want to keep doing these small percentages here. If we split it, so 95 divided by 2, then from here to here is 47.5% on each side here. But if I want just the little pieces, like just this orange color, it's 13.5. Okay. And then within a third standard deviation, 99.7% of the data is covered. All right. So if I do 99.7 and divide that by 2, I get 49.85. But I want that little chunk. So let's subtract off the two pieces. So we get 2.35 for this darker orange. Okay. That might be helpful. That might not. Let's see. If the data is normally distributed with a mean of 8 and a standard deviation of 2, what percent of the data falls between 4 and 12? All right, so what I like to do for this example here, I can draw a bell curve if I want to, but I really just need the mean of 8. And then I can draw out my standard deviations, right? So within one standard deviation, I go to the right all the way and then to the left all the way. So I can go out 3. Standard deviation is 2. So 8 plus 2 is 10. Plus 2 is 12. And plus a third is 14. And then I'll go the other side. So this time I'll just subtract 2. So 6, 4, and 2. And the question is asking for between 4 and 12. So 4 and 12. So if I think about where that was in relation to the mean, right? Mean is 8. So this was 1, 2 standard deviations on each side. So 2 standard deviations, which goes with the 95. 95% of the data is between 4 and 12. Let's do it again for another scenario. So normally distributed, a mean of 25, standard deviation of 5. What percent of the data is between 20 and 30? All right, so I have a mean of 25, and then I have a standard deviation of 5. So I'm going to go the 3 above and 3 below. So 30, 35, 40, 20, 15, 10. So you can stop when you get to the data values of interest because it wants 20 and 30. So I could have stopped at the first, but I like to do all 3, right? So it is within that one standard deviation. So that means we only have 68% of the data with that. Okay, let's look at the third one. So if normally distributed, a mean of 200 and a standard deviation of 15, what percent falls between 155 and 245? Well, let's find it. So we're adding 15 each time. So 215, 230, and then 245. So 245 is that upper bound here. So I am within 3 standard deviations. I'm going to check the other side though. So let's see that other side. If I subtract 15, I get 185. Subtract 15 again, 170. And then subtract 15 one more time for 155. So it is within 3 on each side. Then that goes with 99.7% of the data. Okay. So let's go a different direction and say that we have the mean, the standard deviation, and we want to know what two values does it fall between. So we want 68% of the data for this first one here. All right. So 68% of the data is one standard deviation on each side. So if I have a mean of 100 and a standard deviation of 20, so 120 and 80, then there's my range, 80 and 120. All right, I'm going to erase this to use this same space here. So that second one, so we have, it's standardized. So it's normal with a mean, well, I shouldn't say that because that's standard deviation of 15. So we have a mean of 0, standard deviation of 15, and we want 95%. So that's 2 standard deviations on each side. So 15 and 30, negative 15, negative 30. So between negative 30 and 30. All right, let's do this third one here. So we have a mean of 14 and a standard deviation of 2, and we want to go that 99.7, so those 3 spots on either side. So let's add 2, so 16, 18, 20, and then was that 12, 10, 8. So we'd be between 8 and 20. Okay. Okay, so standardized scores. So these are those z-scores I was kind of mentioning earlier. So we can turn the data values into these standardized scores just to help us compare different data sets, right? It would be easier to look at z-scores when comparing. So let's just look at what they are, okay? So to standardize a score, we take the data value, right? And then we're going to subtract, here, I'll just write this on here, data value. We're going to subtract the mean. And then we're going to divide by the standard deviation. And then that gives us the z-score for that one specific data value. And what that z-score tells us is how far away we are from the mean. So if we get a score of like 1.2, then we are 1.2 above the mean. But if we get something like negative 2.3, then we are 2.3 below the mean. So that positive and negative just tells us if we are above or below. If we don't know the actual data value, we can rearrange this equation with some algebra here and solve for x. So I'm going to show that instead of just leaving it at just believe this. So I have z equals x minus the mean over standard deviation. So I would have to multiply both sides by the standard deviation. So I've got standard deviation times z equals x minus the mean. And I want to add the mean to both sides. So x equals standard deviation times the score plus the mean, which is right here. This just says mean plus and then z times standard deviation. It's the same thing. So let's actually find some, okay? So suppose we have data that's normally distributed with a mean of 50 and a standard deviation of 6. So compute the standardized score. Round of 3 decimal places. Okay, so the first one is, let's see, the z-score is data value, so 52, minus the mean, which is 50, all over the standard deviation, which is 6. I can type that in a calculator. 52 minus 50 is 2. 2 divided by 6 is 1/3, which is 0.3 repeating. So we are 0.3 above the mean. All right, second one, let's do 40. 40 minus 50 over 6. So it's negative 10 over 6. So it's negative 1.6 repeating. So we're below the mean. And that third one, 68 minus 50 over 6. What is that? 18. 18 over 6 is 3. I don't have any examples where we're finding the data value, so let's go ahead and do that. I'll write a little heading here. So how about standardized score 2, original data value. So let's say we have a mean of 10 and a standard deviation of 2. And let's say the z-score we get is 1.4. So find the original data value. Find original data value. Okay, well, I had that formula, right? Data value was the mean plus the z-score times the standard deviation. So we had a mean of 10. The z-score is 1.4, and the standard deviation is 2. All right. So let's plug that in a calculator. So 1.4 times 2 plus 10 gives me 12.8. Right? So really, I'm a visual person, so this is what I see. I see our mean is 10, and we were told that the standardized score is 1.4. So I am above the mean, right? Because 1.4 is positive. And so what I want to find is like exactly how far. So I can take that standardized score and multiply by the standard deviation. And then that piece right here is actually the distance from the mean to tell us how far to go above it. So it's kind of cool. So, all right, if you have any questions, let me know.